So I'd like to first off thank Mohammed, Craig, Jacob for organizing this activity. This is an experiment in some ways about how you would experiment at NSF. This is actually a pilot for us to be able to look at how might we be able to create change and be able to produce a lasting, sustaining transformation. And I'm very pleased with both the attendance that we have here as well as the great, I'd say, variety of schools that are represented and the different demographic regions that we're touching upon. I think this is really cool. This activity is one where we started to be able to try and put together something along these lines. I think it was probably about 2.5 years ago where the first discussions of this took place, and I certainly was open to the idea, and I want to actually publicly thank the Cognizant Program Officer of this, which is Dr. Susan Finger, because she was the one who actually is responsible for funding this activity. But the discussions that took place originally was how might we be able to do something that would really have an impact across the HBCUs, not just in a single HBCU. And so my deal, if you will, with the group was, okay, let's try something, but you have to have all the HBCUs participate. So that was essentially the requirement. I think I'm quite impressed by the fact that we have the group together today that have been willing to come together and share your knowledge and be able to really leverage each other's capabilities. So this is hopefully exciting for everyone as it is for NSF, and we're hoping that this could become a type of model that we would be able to use as a change agent type of model to be able to really try and impact undergraduate STEM education. So that's sort of my NSF background speech. So now I'm going to veer off a little bit because Mohammed asked me to be able to say a few words about sort of the humble beginnings that this activity had. And so recently, someone asked me, so Don, why are you so interested in this innovation stuff? This was something that took place recently at the ASEE conference. And it's an individual that I've worked with over the years, but he said, well, why is it that you're so interested in this innovation rather than just spending your time on the education? And I thought about that, and I said, so where does this really come from? And I have to say, it sort of crystallized when I happened to just be looking at a slide when somebody said, there are those that really think about things. And so you have some students in your class, you probably all know who they are, right? They come in and on day one, they start asking you questions about what it is you're doing. And those are the types of questions that you might not have an immediate answer to, but you say, I'll have to think about that. Then there are those that about 2-3 weeks into the course, you have your first lab. And there are a couple of students who have used the equipment in a way that shows they've been very conversant with being able to play with this stuff in their past. So there are those who think and those that tinker, and to me, it sort of gelled when I said, well, those are the thinkers. The ones who are actually able to allow their minds to be able to be creative, to be innovative, to be able to play with stuff in ways where they're able to organize their information. And when they do so, they don't just work on problems that are basically stuck in the box, but they can think a little bit more outside the box by identifying the problems and develop solutions. So, the problem that we have with all this is that the students are coming into, how many of you teach freshman courses? Okay. And I'm going to apologize right now, but this is going to be an interactive session, so you don't get to just part of the price for coming is you have to deal with me asking you questions. So, what course is it?
C++.
C++. Others?
Engineering, freshman engineering.
Freshman engineering. Do you have circuits involved in that at all? Any electronics aspects?
Yes, it does in their design.
In their
Freshman
design.
And the whole idea is to always not to know the problem ahead of time. Talk about the process of dealing with solving problems, forming teams, production, and then get someone from the aviation department to pose the problem. And then from there, the teams at development will begin to solve that problem.
Great. And then you come up with
And
some
then
sort of
if we
solution.
involve electronics, then electronics.
Got it. Great. Others? So, yes.
It's a course called Practicum, and it's pretty much focused on the kinds of things that you're interested in. It's got a blend of basic understanding of concepts like simple test equipment, and then it gets into primitive circuit elements and transducing elements, and then actually electronic systems by the end. So it sort of gives them an acquaintance with the field without having a formal understanding of how to tackle mathematics.
Got it. And this is
What's more phenomenal?
first semester or second?
First semester.
Oh, that's cool. Yep. Any others? Yeah.
We have a course called Introduction to Engineering. It's got a variety of students, not just electrical engineering students, but it's got business students, for example. In fact, the majority.
The majority are business folks. Ah, right for the picking. I love that. All right.
So it's kind of different, and we try to teach a little bit of several different engineering programs.
Oh, that's great.
Electrical, mechanical, chemical.
Can you
But-
Yeah. So he teaches a course where it exposes the students to a variety of different engineering types of activities, programs, electrical, chemical, ranges through it. The predominance of students might actually come from the business area rather than the engineering area. So I'm going to set the ground rules here. How many of you in this room are not electrical engineers? Okay. And how many of you are not interested in increasing the number of electrical engineers?
Bring one small caveat.
Yeah.
So my bachelor's, master's, PhD are all electrical engineering. I started off on the faculty of Illinois in electrical engineering. Now I'm in a bioengineering department.
Wait, those are you're a brother.
Oh,
Yeah,
we-
biomed is cool. Yeah,
Biomed.
that's cool. I just wanted to set the stage here because I have a pretty strong agenda, and that is electrical engineering enrollments are falling, and I don't get it. Now, admittedly, I'm an electrical engineer who started as a biomedical engineer. I saw the light. Anyway, I really don't get it because a lot of what is necessary today, and now thank you for this, but the next world that I see being a real viable, rich space for us is the merger of biology and electronics. You know, we're getting close to the point where we're going to have the opportunity to be able to not just sense, but activate. And be able to actually create nervous intervention and be able to control systems the same way we do right now with mechanical, electrical systems. We'll be able to do this with electrical, biological systems. And so this is a rich opportunity. So why I go through this whole diatribe is we suffer, even in these first courses, with all due respect, we're doing with phenomenological types of models. We're trying to get them at least aware of what the dictionary may be, what the appearance of parts are may be, what they might actually look like. But the problem that we have, and I apologize if some of you have seen this, is that when they go through K through 12 training, we give them some input, we give them some system, and we ask them to be able to get the output. And the students are probably coming in, if you constrain the types of problems, better than they ever have been at being able to go from, here's the input, here's the system, tell me what the output is. And they're pretty good at being able to tell you the output, particularly if you let them use their calculators or their phones. Well, the problem is, in their career, you're given an input from a set of specifications, design specs, or what have you, what the system needs to be. There's an output that you have as a desired response that you're trying to be able to actually affect. And what you're asked to do is not plow through from left to right, but to be able to actually pick out and create what's in the middle. How do you get from a particular set of criteria to a system's output? So this is the problem, because they come in to your classrooms and the students aren't necessarily trained in this type of thinking. They're not trained to be able to look at systems from this. So there's a clear dichotomy in what goes on. They're taught to be able to solve problems using a pretty clearly well-defined type of process. But in the workplace, most of the types of activities that a graduate or teams of graduate or what have you, their first types of approaches are usually ill-defined. The teacher doesn't give them a homework assignment. It's usually go off and create a system that will actually do this. That's the type of thing you're structuring your environment to be able to do. And they lack a predefined path to a solution. And students come in with the expectation that there's always a predefined path, and you just need to be able to show me what that is. And what's even more problematic is with the No Child Left Untested activities that we're involved in right now, we have, in essence, this built-in type of mentality that what I'm going to be doing is, in essence, doing template matching. So I just need to go to the book, find the example that's most like the problem that you've just given me, and I'll be able to then come up with the answer. That's not what real engineering is all about. So anyway, just as a quick background for this, Daniel Pink did a study of this creativity ranking. And he actually looked at a series, or he asked for responses from a series of engineering faculty in academia and industry representatives. And they asked them to rank what you would see as being important in terms of career types of skills and activities. So one that's interesting to me, number one for industry was not problem solving, it was actually identifying a problem or being able to articulate a problem. And what was most important to academics? That was problem solving, which was way down the list in terms of industry. So there's even further dichotomy that exists across this. I know this is difficult to see, but I'll basically share what's part of this. So this was a study that we funded at NSF to be able to look at what industry needs. It was called Transforming Undergraduate Engineering Education. Phase 1 was bringing in industry and asking them, what are the real skills, knowledge, ability that you want your students to be able to, your incoming employees to have graduating students? Well, if you look at this, the blue bars are what they felt was important today, and the orange bars is what they felt was important 10 years from now, and the green bars is their assessment, this is again industry's assessment, of what is the quality of the education in that area. And I think you can see that there are some issues that we may have associated with this. So, for example, the green bars associated with some real, well, we'll forget about foreign language skills for a moment, but if you look at synthesis, synthesizing engineering concepts, having some sense of business activities, being good communicators, having interpersonal team skills are unfortunately not necessarily being rated as high quality, let's say high quality training from the academic institutions. As I look through the same type of chart where there's, again, the blue is what's there today, orange is 10 years from now, you can see some disparities in terms of this. The largest ones are in the area of innovation and creativity. And then when we look at the green areas of where we really need to improve our quality of education, again, this is measured by the industry, you see that the entrepreneurial aspect and the flexibility to be able to adapt to changes that may come down the pike are rated poorer in those regards. Now, those are real problems because the students, to be able to keep our country's engine going, our innovation engine, we need to have creative ideas. So that's a key problem. So this is just sort of a basis of problem-solving chart. So I'm not going to get into this too much, but just to say that what we typically do is break things down into sort of plug and chug that are the easiest problems. They're structured. They're the types of things that students will be able to do their template matching and be able to do a good job of. That's over on this bottom left-hand side. The toughest part is on the top right-hand side. And when we look at what we actually expose students to, in the freshman year, they're moving in the lower left-hand portion of this grid, where they're working on pretty much example problems that they have. They may be exposed to some labs in those activities. There's some plug and chug problems. In the sophomore year, we may expand this out so that they become a little less structured in the way the problems are posed. We may actually bring in some case studies of relevant examples that may come from it. Junior year, you start doing work that actually does involve some inquiry and starts bringing in some modeling and offers the students an opportunity to be able to look at greater complexity because they have greater depth of knowledge in their field. But not until their senior year do we actually start looking at the brainstorming aspect of what you do, or, again, up to the upper right, real authentic design problems where, like you said, you bring in folks from industry and you say from avionics or the aerospace, here's a really rich context for you to be able to develop a system or a project around, and we want to do this. So this is just a way to map it, and my encouragement to you is to look at how you might restructure the 4 years so that there's more that moves up towards that top right earlier on in the student's degree program. Okay, so where the mobile studio activities can come into play, which is the whole point of why I'm here. And this is really an opportunity to be able to take a lot of things that may not seem like they belong together, but they may be sort of the MacGyver type of systems. Am I just dating myself there? Where, you take a hairpin, a spool of thread, and you build the Empire State Building, something like that. It was a television show. It was a little bit unrealistic. But anyway, so you get a whole variety of things. This happens to be a kit that was given to MIT students, and they're actually asked to be able to solve problems using this type of material. My experience has always been trying to be able to deal with puzzles. So as a kid, I played with puzzles a lot, but the types of puzzles I played with was what could I actually make from this? And as I go forward, I'll tell you the secret to my career, if there was any secret, or if I could claim any success, was that early on, I had some key childhood toys. And to be honest, my first toy that was pretty much my go-to experience during the afternoon after school was this thing called an erector set. How many of you had an erector set? Okay. So today we call this VEX. And now the reason is, why this went away is because the lawyers got their hands all over, or more importantly, maybe their children did, over these metal parts that could become swords. And unfortunately, people got cut and they got sued, and so they stopped building erector sets. Now they make them with other materials. But I was able to make, by the way, I never made that Ferris wheel, just for disclosure. But I did play with all this stuff, and I took this motor apart, which was really cool because you could pull the case off of it and actually play with all the gears that were inside it. Anyway, that was my first toy. My second toy, if you just call you back to this slide where I had things that don't necessarily look like they fit together, I had an erector set and I had a guitar. And so these were sort of my background, and the guitar was, in essence, my opportunity. As soon as I figured out you could plug the guitar into an amplifier, and there was actually an opportunity to be the loudest player in the band with this type of thing, that really intrigued me. A little later, I had some other toys that I played with as my PhD, was to be able to actually create an electrical pathway. But why I actually went through all of this gave me an opportunity to be able to take disparate pieces, my music, my career, my electronics, allowed me, there's the point to this, allowed me to be able to provide this rich context to the students when I walked into the classroom. And I think all of you in this room do this in one form or another. You bring your own life experiences into the classroom. Why this is so important is it gives the students an opportunity to be able to hang their knowledge hangers onto something called sense and meaning. It gives them sense and meaning. Why it had sense and meaning to me when I cracked open my guitar in my classroom and I literally would take it apart and show all the students the parts in it, that gave them the sense of what an inductor was in circuits. It gave them a sense of what a capacitor was, because I'd open it up and I'd show them the physical capacitor, I'd show them the potentiometer, and I'd vary the tonality of what was taking place to it. And we would do this in a way where they understood that at the end, you could produce something else that may not seem related with music from this device. And by the way, it also allowed me to be able to start teaching things like signals. I had sine waves coming out of my guitar. I process those sine waves. How does the frequency response change as I do different things? So I was able to utilize that. All right, well, back in 2000, I was running a research center on our campus, and Ken Connor was the department chair at RPI, and he asked me if I would be willing to teach circuits again. And I hadn't taught circuits, I don't know, maybe 5 years, 6 years. So I was coming back into it, and what I had been doing before that, I wrote a proposal with his predecessor chair to be able to outfit the classroom with equipment. So we created a studio classroom, and we had a whole pile of equipment that was in it. But when I started teaching in that time, it was really eye-opening to me, because 20 years prior, when I was going through my career and learning basic circuits and electronics, I had gone into that classroom. You saw the erector set. You sort of saw the guitar. I had played with all that stuff. I had my own scope, believe it or not, back in 1960. Okay, old. And I was playing with those things before I walked in, so I had more of a physical intuition of what things look like, what I would expect to be able to see. Students came into my classroom at that time, they had no physical intuition because most of what they were doing were in a virtual space. It was on a computer, it wasn't necessarily cracking things open. You crack open your iPhone, what do you see? A big hunk of plastic with some metal coming out of it. Maybe. Some of it might even be encapsulated at this point, so you don't even get to see that. So that was a problem. And furthermore, I found that the students really needed to be able to have time to play with stuff. They weren't tinkering like my predecessors did and what my cohort did when we were in college. We went into the labs and we were building stuff just to be able to learn how to be able to build something or what the output might be. So they needed those further opportunities. So if I look at where we are today now, we have, oh gosh, it seems like we still need to be able to give them a physical intuition. And oh, they still need time to play. So I guess my point here is nothing's changed in the 14 years since I created this slide because you're all here saying we want to be able to do these same kinds of things. So back then, this was the instrumentation set we had. How many of you have separate labs? Separate labs to be able to run your classes. How many of you run your courses in the same room as the laboratory? How many of you combine lecture and lab? Okay, so there's still work to be done here, but that was the basis behind Studio, was to be able to put the lecture session, the problem session, the lab session, all in the same physical space. So that if you wanted to be able to say to someone, let's build that, people could turn around and do that. Unfortunately, back then, the equipment cost around $13,000 to be able to outfit each one of these stations. And it wasn't portable, and students weren't going to take it home, and all sorts of those types of things. So that's what we said back in 2000, actually. It's hard to believe. It was 14 years ago now. I started thinking about how could we give students the opportunity to do this at any place and any time. And in particular, the one area that I was really interested in being able to tap into was the actual student union. Because I was recognizing that's where students were spending the most of the time actually reading through their materials and actually working on problems together and playing with stuff. So I wanted to build something that would allow them the ability to do that. We came up with the Mobile Studio project. And by the way, this is my partner in crime, Jason Kudermarsh. He was my undergraduate research student at the time. And he was an exceptional student. He's now an exceptional engineer working at Analog Devices. A brilliant student in being able to tinker with stuff. Not the best theoretician, but boy, I'd take him over anyone else on my project team if I could get him. Because he could actually do stuff. And he walked into my classroom having a full suite of bench equipment that was probably better than what we had in the studio in his dorm room. So he helped me build the circuit, and we were off and running. So that was back in 2000 where we started playing with it. Mohammed was correct, and back in 2006, 2005, I think, we came to Howard, and we had packed up a whole series of breadboards. And on those breadboards, again, it's a little hard for me to be able to imagine. It was only 9 years ago, but we were having difficulty getting processors that could do this in real time, that could actually read in a signal and display a signal, pump out the system in real time back then. So we put them all on breadboards. Students worked with the processors set up as a breadboarded Mobile Studio board. And we did that in the classroom. And then we gave them a series of circuits to be able to work on. I'm going to talk about one of them. But now I'd like to be able to just open up this more of a discussion format and be able to say, if I were now teaching today this problem that's on the board. So, if you look at it, it's just got 3 resistors and a DC power supply. So I have a 12-volt source. I have basically a 3K, 2K, and 1K, 6K worth of resistance. So if I were teaching this today, I wouldn't do what I did when I first started teaching circuits, when Ken brought me back in 2000. That was, okay, let's set up some equations. So let's see, I have an input, V in, 12 volts. That has to equal, and I know from physics, and I remember from physics, Kirchhoff's voltage law, so I have to sum the voltages around the loop. So that's equal to I times R1, I times R2, I times R3. If I sum those together, I get the 12 volts. That's not how I would do it. What I would try to do today is I'd say, okay, everybody, let's take out our boards. And tell me, what is the voltage that you measure across R2? Now, let's just play this out. Why would I pick R2?
It's in R1 and R3.
Pardon?
Size-wise, it's between R1 and R3.
It's in between R1 and R3. But why is that important to you? Frame of reference, okay. Okay.
It includes neither the ground or the positive end of the power supply.
Okay, so it's physically disparate from those points, right? Yeah. Now, so in truth, does it matter? No. Students get that? When they first approach this, what do they focus on? They focus on geometry, don't they? They look at this type of problem and they start saying, well, where these things are located are really significant. Why is that? It's because that's how they've been trained. They look at things and they try and be able to associate this with something that they've seen before. So why I would ask them immediately to be able to look at R2 and measure the voltage. And if I'm correct, they should see 4 volts across it. And then say, what is the current that's flowing through it? Is I would want them to be more inquisitive about this and build into it. So tell me, build the circuit and tell me what's the voltage across R2. And then I'd say, what's the voltage that you measure across R3? And what's the voltage that you measure across R1? And ask them to construct an equation. Not give them the equation, but ask them to construct the equation that actually describes the relationship that you're seeing between that voltage, the resistance, and ultimately knowing that we have 6K of resistance, we have 2 amps of good, 2 milliamps of current, therefore that's what's flowing throughout the entire circuit. And interestingly enough, that current stays the same. And they should be able to discover that. So I'd like you to be thinking about, when you create your types of examples that you're going to be teaching, flipping this. Not flipping the classroom from the standpoint of video versus lecture. Flipping it from the standpoint of trying to be able to give the students the opportunity to discover these things rather than trying to be able to feed them these things. Now, again, back in 2000, I was feeding them information. I was feeding them formulas, and I was realizing that they weren't necessarily grasping the intuition of how to be able to apply that. And more importantly, if I change this from the simple circuit to something that might look, now I have the same number of elements, and I ask them to be able to tell me now what's going on with this and make measurements across this, they'd be able to now recognize, okay, so the topology, the geometry of the circuit looks the same. However, I may have to be able to look at this a little differently because I don't have 3 of the same elements in the circuit. So now I'm going to ask you, what do you see in this circuit? How would you approach if somebody asked you, what's the voltage that I would see in the circuit across what's labeled L2, how would you do that? Pardon?
L1.
I'm sorry, L1. It wasn't a trick question.
You have to give the students.
I was trying to see if you're awake.
That's if I'm a freshman.
Yeah.
If I'm a freshman, I'll probably observe it.
Which is?
Put a scope across that conductor and watch it phenomenal logic. Because I don't, probably at that point, I probably don't have the calculus.
Okay.
And time process.
That's good. Okay. And you just said something that fascinated me when I watched students. Putting a scope across L1. Is that easy to do?
It is if you have a differential scope change.
Ah. So therein lies another piece, that you can use this as a teachable moment. Where, if you stick the ground of the scope probe on the right side of L1, all of a sudden you don't have the right measurement that you want to be able to make. So if I wanted to be able to have a student understand what's taking place, I can ask them to do these types of observations. Look at what you see across L1. Look at what you see across the capacitor. Look at what you see across the resistor. And then be able to give them a sense of how the current is still the same flowing through the circuit, but the voltages still add up like they did with the resistive circuit, because that Kirchhoff's law thing still is in existence. However, we may have a further perturbation here, which is something that you probably immediately recognize as being phase comes into play. That they'll see on the scope, that they'll be able to observe. And that, again, I found gave students more intuition in terms of what they were studying than if they were just going through and I was trying to give them the formula. So, we had set a number of learning objectives for this, where we were asking them to be able to understand what the damping was, what's the natural response of the system, give them a sense of what the picture looks like for under-damped conditions, over-damped conditions, critically damped condition. Look at what's the relationship between time and frequency. Look at how resonance might be related to the circuit elements that you have in the circuit. And furthermore, ultimately, and this is where I was moving towards, if you remember, the complexity of the problem that we were dealing with and the more creative aspect of what you were trying to be able to imbue in the students. Ultimately, you ask the students to be able to design some type of tone circuit, and I would actually have a guitar. Now, the guitar didn't look like a guitar. It was actually a string of a guitar that was just suspended by two metal prongs on a piece of plexiglass. And the advanced guitar had a tuner on it, and then the super advanced guitar that I think Ken may actually talk about by Donnie Ferry at Georgia Tech allows you to even have frets and tune the thing, right? Yeah. So this was just a simple plexiglass, but students could pluck it with an inductor that was underneath it. And that inductor was basically just a magnet that had a pile of wire wrapped around it. How did we wrap the wire around it? We took a drill, and we just turned it to the drill. So you got 200 turns around it. Before you knew it, you had plenty of signal. So that allowed me to be able to explore these types of activities and be able to allow the students the opportunity to be able to look at those outcomes. We asked them to be able to do this with P-Spice. We asked them to be able to explore this. And at the same time, then we had them hook it up. This is the old mobile studio software. It's funny to say that, the old mobile studio software. It's already 4 years old. But this allowed them to be able to look at that underdamped condition where you started seeing the overshoot take place. How did they do that? Well, they changed the resistor on the circuit and dialed in the amount of damping because, of course, the resistance is directly related to that. So these were things that we had. And now I'm going to bring up this piece and acknowledge who I blatantly stole this from, which is Charles Kim, to be able to actually run a design experiment where you ask the students to be able to now build a circuit and actually analyze the circuit at the same time. But it had a purpose, which is once you build the circuit, and this is a band axle filter, be able to look at how does that change the music coming from your iPod or your iPhone or your device, take the music out of it, pump it into that circuit, and listen to the output on a speaker. And so we did that, and that's what Mohammed was referring to. Back in 2005, we took an empty room. We set it up with benches like you see here. We distributed components, and Tim was kind enough to be able to help me out in terms of being able to do this. We started with, it was literally a bare room at 7:30 or whatever. We started putting in the tables. 8 o'clock, we had this room set up. And by 10 o'clock, it was only 2 hours, wasn't it? 2 hours. Fanta? Yep. So that was a student. And you can even see in this picture, that's the crude mobile studio, by the way. That was the first instantiation of it. Little historical reference. That was the ProBoard version of the mobile studio. But by 10 o'clock, she had that circuit working, and you can see the speaker there. You can't hear it. I don't have audio. But about a half an hour later, she marches down into his office. What'd she say to you?
Well, she said, we need to hire this guy.
No, that wasn't what I meant.
She told me what to do. She said, number one, why are we not doing this? And number two, you need to hire him. Of course, he didn't want to stay.
Well, look, it wasn't about the hiring. The point was she actually had a working circuit and was so excited about being able to hear how the circuit changed her song, her music, that it actually provided her with sense and meaning to why it is she was doing what she was doing. So I encourage you to try and do these types of experiments, things that really do have meaning to the student population and often give them sense. Ken had produced some of these balance beams. Well, they're not balanced, but they're beams that you can thwack. That's a technical term. But you basically thwack the beam. It creates, in essence, a mechanical response that's picked up by a couple of sensors that you might have here. And the students are asked to be able to build circuitry that allows them to be able to determine, in essence, what the response of the system would look like, and then by getting the response of the system, they can go back in and back calculate the mass of the beam from being able to correlate the electrical signal that you have with the mechanical system. Now, why this actually is interesting, this is the type of activities that I think a couple of you described that you're employing. This maybe not this complex, but something similar in your freshman experiences. And so here's where something like the mobile studio activity can provide you with a rich opportunity to be able to do that in early on in the students' careers. This was the teaching environment that I actually taught in when I was back at RPI. We had about actually 90 students packed in there at one time in a maximum. It was still 2 teaching assistants and myself. The beautiful thing about this, and I encourage you to think about the physical environments that you're going to be running your experiments in, is you'll happen to notice, forget about those screens because they weren't there. Replace those screens with a laptop, for example. Every station has a student laptop. They had a mobile studio board, so they didn't have much desk space that was taken up. But the beauty of it is I could walk around and I could pretty much make eye contact with all the students simultaneously. Well, not simultaneously, but scan very quickly around the room to see what's going on. Likewise, we could walk back around it and see everyone's screens to be able to see what they're doing. This provided the students with a rather rich opportunity. So this is where I had some questions. And so we had brought in the assessment folks to be able to say, are we doing things in a way that the students are actually gaining some benefit out of this? And Diana was kind enough to be able to offer at that time her services, and what was very unique is one of her PhD students, if I'm telling this story wrong, please tell me, but one of her PhD students came and sat into this room and basically took the whole course. So she sat through every one of the lectures and observed what was going on with the students. And this was fascinating. Why? Because I would give my lecture, or we would do our experience, we would go through this, and I'd meet with her afterward, and she'd pull me aside and say, do you know what they were doing? And I said, yeah, I told them what to do, and they did it. And she said, no, not really. What was really happening, and it happened to be, remember that RLC circuit problem? We asked them to be able to set it up and sweep the frequency. So, I can't remember what the topology was, but let's say you take the voltage across the capacitor of an RLC circuit. What you've created is in effect a low-pass filter by taking the voltage across the capacitor. So the low frequencies pass, the high frequencies get cut off, right? Okay, so what we asked the students to do was sweep the frequency of the mobile studio to be able to see where that cutoff started occurring. What would they do? Well, I thought that they would tell me what the cutoff was. Turns out that wasn't what they were interested in at all. And her colleague came to me afterward and says, that's not what they're doing. What they're doing is they happen to recognize there's this one frequency, which is the resonant frequency, where all of a sudden they have a greater output than what they had at the input. And they're all playing right around that frequency, trying to be able to figure out what's going on. That's the beauty of having folks from assessment who don't really have the background in the technology, but can actually keep an eye out on what's going on and allow you to do formative activities as you go through your experience. So what did I do the next time after she told me that? I said, okay, let's set up the circuit, and I'd like you to put in this frequency, picking the resonant frequency. And what did I do then? I said to the students, take the voltage, and to get around the ground problem, I had to take the voltage across the capacitor with respect to ground, so I didn't have to deal with that differential. But I said, tell me what's the voltage across the capacitor? And let's just say the amplitude of the input was 1 volt, and the output was 2 volts. And I would ask them, where did that other volt come from? How did you get more at the output than what you had at the input? Did we just defy a basic law of conservation? Did we just make something that's there? And I have to say, that changed the way I taught that material to the point where I focused on what their assessment individual was telling me was the students' activity that was going on in that classroom. That they were actually more interested in that unique band of frequencies where the output jumped up than they were in what took place before or after. Now, it might have been different if I had music playing through it. And oftentimes, by the time I ended, I would pick up my guitar and I'd play a song, just to put them through more pain and anguish. And they would actually then go through and build their own circuits. But that was fascinating, and it did change things to the point where in a typical exam that I would have given before that time would have been one where here's a circuit, tell me what the voltage at the output is from this. That was something that you would ask them to do. Or tell me what V out over T looks like. So they would have to calculate it from the circuit. But after that experience, what I did was I decided to run a test. And so on a midterm circuits problem, that's the graphs I gave the students on the exam. And then I gave them a circuit that looked like this. And I asked them, instead of telling me what the output was, because they saw the output in the graphs in this problem, I said, instead, tell me what capacitor and what resistor and this resistor would produce that output. So I flipped it from an analysis problem, or a strict analysis. Again, given the input, here's the circuit, tell me the output. I flipped it to, here's the input, here's the output that I want. Design the circuit or the system to be able to give me that output. And the fascinating thing was we were able to run this class pretty much the same for about 4 years? About 4 years. So I had a whole pile of longitudinal data that I was able to use. The first year, the average on this problem was probably, as I remember, it was more like 7 out of 20. The first year. And then as we went forward, I wouldn't give the same exact problem. I'd change this around. Sometimes it would be taking the voltage across the inductor, sometimes capacitor, sometimes it would still be a notch filter or a bandpass filter, depending on how I took it. And what ended up is, I think it was at the end of year 2, the results of this problem moved from 7 out of 20 to something like 16 out of 20. And the students had a much better ability on the final exam when I would give them an open-ended problem saying, design a circuit to produce this kind of output. Totally up to them what they wanted to do in terms of the circuit, what components. I would limit the number of components that they had to be able to work with somewhat artificially, but not too much. They ended up with 17 out of 20, as I remember it, on the final exam. Yeah.
How would you, when they design their own circuit, how would you justify it?
So,
Their TAs.
so the answer,
They put out a relationship.
yeah. So this was a problem because I graded every single one of them. So it was close to I think 110 students, and on the final exam, I had to grade every single one of those problems because I didn't want to depend upon the TAs having to look at all of the different permutations that you could actually end up with. Now, if they got close and they didn't have, if there was something just a tiny bit askew, but the conceptual understanding was there, they generally got full credit. But if there was something where they were really missing a concept, for example, wrong frequency band, or the gain wasn't even close. The problem that I just showed you, I think there was gain in the system, so RF has to be greater than 10K to be able to get that. Or if the gain is 2, I guess RF could equal 10K. But I actually had that 5 points off, 10 points off, that type of, I had created a rubric for it, but I would give them some latitude around those ends. Yeah.
Another point that's interesting about this approach, this provides a segue into statistics, because what you're doing is you're looking at the output, you're asking what explanation gives rise to the output. That's exactly what we do in statistics. So this would be a very nice way to be the gateway drug.
There you go. Great. That's wonderful. Yeah.
I think you raised a good point in the sense that I think over many years, faculty have found out it's much easier to grade analysis than it is synthesis. And as a result, they're conditioned to teach analysis.
Yes. Well, let's just be thankful that most schools don't have scantrons. But it is, it's a challenge in terms of time, but I can tell you it's a worthwhile opportunity. And I can tell you all sorts of stories, but I won't bore you around them, of students that, but one other requirement I had is if a student got below a 60 on the first exam, they had to come to my office hour before they got to take the second exam. And then if they did it on the second exam, they had to come for twice as many times after the first exam. By the time the third exam rolled around, the students would either drop or they'd be in my office so much that, I just, give them a desk. But it worked out pretty well. Okay, so there's a lot of good news, I think, that we're facing right now. MOOCs, it's funny, I saw an article today on the Metro over here about how the MOOC has disappeared, and yet it was the hottest thing a year ago. But I don't think that's true. But when we look at this, right now, PCAST report and the current activities over at Office of Science and Technology Policy are laser focused on STEM education right now. I can tell you this with personal experience. I was over at OSTP a week ago with Tom Khalil, and his interest is actually quite intriguing. His interest is to be able to actually create in essence, a payment assessment. So, what do I mean by that? His story around this is to be able to eradicate a certain form of malaria. What they were doing was actually working with drug companies to be able to create a drug for an area of the world where people can't afford it or wouldn't necessarily provide a huge market. So they worked with the drug companies and said, this is what we'll do. If you create this vaccination, which is a derivative of another vaccination, we'll guarantee you payment for X amount of this type of stuff. And therefore, the drug companies were willing to be able to do this, whereas if there wasn't that guarantee of payment, they wouldn't invest to be able to build up that vaccine, the amounts that were necessary to actually put that into production, because there's so many more profitable opportunities that they might have down the path. So what they built in was this incentive. Why I offer this is because he's thinking, let's fix 5th grade math. And we'll do this by, if the students on the U.S. increase the PISA scores to some percentage, where we've now moved up by, let's say, 5% per year, then we'll give someone compensation for that improvement. Or another way to play this, if we increase the number of electrical engineering graduates coming from HBCUs in the next 5 years by 10%, we'll provide 2 HBCUs a financial incentive for doing so. So there's a guaranteed payment if you could actually meet the project goal. And this administration is now at the point where they're thinking about this as being some type of methodology, and I will hopefully be back here on Thursday to be able to tell you about some of the NSF programs. So here's the thing. We wanted to be able to build into this a model where you'll be able to explore these opportunities, think of great ideas, and then at the end, why would you put in all the time and the effort? Okay, yes, it's all about the students. That's why we're here. But in the end, there's also this other piece. What's the incentive program? And so what I hope I will be able to do on Thursday is offer to you what might be some proposal opportunities that you'll have to be able to continue the work that hopefully you'll engage in this workshop. And it sounds to me like you'll have all of the touch points that are necessary. You're going to be able to explore how you might be able to develop new circuit experiences, new electronics experience, new first-year experience, new other experiences that come in other disciplines, other interdisciplinary, multidisciplinary activities, and then how can deans or department chairs impact their entire institutions? So I applaud the department chairs getting together as a group and saying, how can we work together to be able to actually now leverage our abilities across the institutions? Okay, go ahead.
I love the incentive idea. One important piece of that, correct me if I'm wrong though, is not only to incentivize universities, but to, ultimately you got to get the students excited about doing it. So getting some student feedback or students who did succeed, understanding why it was and what intrigued them. So just to get them to be a part of the process, so that ultimately we motivate the students to want to pursue it.
Absolutely. And so I really would love to hear any other thoughts that people have around this. Our initial ones is to be able to work with this series of industry folks that will guarantee jobs.
Along those lines, I'm sure you heard about Jesse Jackson and what he's doing now with Google and everyone in Silicon Valley on the top morning show last week.
Yeah.
So it sounds like Silicon Valley is going to try to spend a lot of time coordinating graduates of HBCUs to increase the number of Americans there.
Well, my hope is that they're not just doing this because of the press that they've been getting, but they really see the value of being able to have a diverse community of engineers who really do think very differently. Not everybody in this room grew up with an active rector set, because of lots of different reasons. But okay, the predominant one is you're not as old as I am, maybe, But you came from a different experience. You may play with other things, great, okay. But it's that richness that we really want to be able to have our industrial ecosystem leveraging. So I'm hoping that that's what the real long-term objective is. Yeah.
So the question I think it would be good.
I can't hear you.
Okay. The question I think it would be good for all of us to think about is, if you look at everything that Don has mentioned, he started out with this idea of students coming in without intuition. What do we mean by intuition? We actually have to think that through, and that gets us to things like concept inventories and all sorts of other things, which are measures of what students know coming into our classes and what we want them to know coming out of our classes and that sort of thing. But I think one of the things to think about, because this has actually come up in other groups that I've been working with, is that we need to be reaching into the high schools, all right? And if you think about the kinds of activities you're developing using these inexpensive platforms, can we put together a kit, a recommendation of a kit, that we get in the hands of the high school students and get them playing, not focusing on doing, elaborate academic stuff before they come, but playing electronics. There's a lot of kids doing robotics, but they do almost nothing at all with electronics. It's a mechanical experience for them. So how do we take what it is that we're working on? And that's one of the reasons why we put outreach as part of the discussion on the last day was many of us do things in the summer. We all have programs for incoming students, and we have programs for recruiting students. How do we take what we're doing here and give the students elsewhere, in the high schools, and we hope in the middle schools and elementary schools, the opportunity to do something that is just playing with electrical and computer engineering concepts. And they don't necessarily, and don't tie yourself to just thinking about mobile studio or analog discovery. Think of the cheapest thing you can come up with. The simplest ideas, the kind of exercises you can, some toys that people can be playing with, whatever they might be, whatever they may have. How can we do this in such a way as to actually impact their intuition coming in? And do they come in are they buying into the EC idea even before they show up?
Well, trying to be able to create a continuum is a laudable effort. so that they don't just see the end of high school and lack of transition. So hopefully Nathan will also talk about some of the bridge program that he's had to be able to actually look at how you take that transition in a different way. I don't want to spend too much more time talking to you, but I want you to get into the good work that I've asked the group to be able to explore. But this is a very different era, and the opportunities that we have as educators are ones where there's so much more knowledge that you can tap into from activities that are going on in terms of brain research. I've been fascinated with these studies with fMRIs where you're able to actually see how different parts of the brain are lighting up for students that actually come from different backgrounds, different experiences, different generational groups, parents that are in the top quarters of their income, parents that are in the lower quarters of the income. And sure enough, when you start looking at these kinds of things coming out of the brain research groups, you start getting a sense of we just want to be able to focus our attention on lighting up specific parts of the brain. So there's a good deal of knowledge that's there that I encourage you to be able to actually leverage. There's also quite a bit of cognitive psychology that we can tap into of what really does work in terms of engaging students. And there's lots of activities that we've funded at NSF to be able to do these. There's problem-based learning, peer-led student learning activities, there's problem-based learning activities, and there's whole hosts of materials around them. Don't spend your time reinventing the wheel. Tap into those. Steal them liberally. Use these ideas and be able to build upon them as you go forward. But there's a rich set of knowledge that I think is viable for you to be able to build into the experiences that you're going to provide with your students. And then there's a whole stream of classroom studies. And so one of the things that hopefully you might touch upon is what type of protocols might be used in the classroom to be able to look at what the engagement level is of your student populations. How are they actually participating, and what are they garnering out of some of those experiences? And there's a whole rich group of folks that are working in this area that have created TDOP, RTOP, these different protocols that will allow you to be able to get a sense of what the student involvement is outside of them just getting the right answer. And I found that the students that just gave me the right answer and then stopped weren't getting as much out of my classes than ones that got the wrong answer and figured out why they got the wrong answer. So you want to be able to take advantage of all of these resources that are out there now. And I guess I'm just going to sort of close with, we have an opportunity to be able to take advantage of shifting from the book, where the book might be now electronic and it might be on the web, and you don't have to buy the textbook anymore. And now I'm going to offer a sort of a heretical comment, and that is, you may very often at this point in time not see students open the book the entire semester. I'm just giving you the reality. So you may think that you wrote the greatest textbook, those of you who are authors, all due respect, but the students today will find a PDF version, possibly illegally, and they'll be using that PDF version for being able to do their studies. And what they really refer to them for is the homework problems that you've assigned out of the book. The other material, they are really adept, at least from what I've observed, of typing in the exact problem statement into Google, and sure enough, something comes up.
That's exactly right.
And what's fascinating about that is never do the neurons leave the brain. I mean, it seems like they never really engage in it. They'll just copy it down and take it as being gospel. And we need to be able to take advantage of, if that's what they're doing, how would we actually utilize that? How can we change the game to be able to understand what that might be valuable about? And then, when we look at what good lecturers can do in the classroom, oftentimes you'll still find the people who really are invested in their student populations and understand their student populations, observe their student populations, relate to those student populations. You can't replace them. I'm sorry, but I've funded a lot of MOOCs, a lot of MOOC activities since I've been at NSF. I'll now tell you, I enjoy getting the material and the knowledge that comes from those studies, but it's not for me. I loved being able to maintain a relationship with my student populations, and I think they got more out of the opportunities to just talk to me about what it is that they were doing than what they might have seen in a lecture. Now, the video snippets to get you over that little conceptual, misconception, that one little understanding, great, I love it. I've looked at lots of Sal Khan videos. I don't know if you guys have seen the Khan Academy materials. If not, just look at one of them. You feel like the guy's sitting right next to you teaching. That's a gift. He's got a gift. He can do that. Not everybody can do that, by the way. And I won't mention any other names, but there are some other circuits videos that don't do that. You don't feel that same engagement in the process. So there are these opportunities, but I don't know that it's ever going to replace the value that you can provide to your student populations as their faculty member. There's a rich set of resources that are available. When I quit out of this, I'm going to show you one that I actually looked at for the first time in 7 years. But we built it 7 years ago, and I'm telling you, I think it still stands up to anything that's produced today. But there's a whole suite of resources now that you should be able to bring into the classroom. I embraced PSpice. I embraced my students' use of it, and I would intentionally give them problems that would actually cause PSpice to be able to fail, so that they would recognize that they can't believe everything that they get out of it immediately, that there are conditions over which things operate. What was beautiful about that is when they did it with the real hardware, they saw where that problem actually existed because of the physical nature of the devices. But there's a whole suite of these that we want to take advantage of, and we want to be able to actually engage the students in this hands-on activity. This happens to be a group of folks in Cameroon. I'm sorry, Ghana. So, your influence will be felt all over the world. And if all of you figure out what that magic ingredient is to be able to engage the HBCU population into engineering and electrical engineering, remember, electrical engineering. I'm kidding. No, I'm not. Then we can take that secret sauce and spread it very rapidly in today's world. And so I want you to be able to have your students really focus on trying to identify problems. I want you to encourage them to tinker and be the innovators of tomorrow. And with that, I'm just going to say thanks, and I'll open it up to be able to show you this one example. This is a module that you can find. It's for the workshop organizers, actually the moderators of this. This is on the academy.rpi.edu site that thankfully hasn't been taken down. But what?
This week.
Oh, this week.
It just disappears every once in a while, and then I get it back.
Oh, well, thank you. And in fact, thank you, because my emails goes up when the thing goes down. But this is just an example. We built this because I wanted something that allowed the students a full tinkering space. So this happens to be one where you can actually define the circuit by whether it has 1 0, 2 0, no zeros, one pole, a single pole or double poles. And you can actually, everything on this, by the way, is movable. so I can move the poles, and it immediately updates and shows me what happens in terms of as I move closer to the y-axis, I reduce damping. You start seeing the function going into an under-damped condition, and you see overshoot. If I put them purely on the axis, I start seeing the single resonant condition that I end up with, and I get to be able to look at the relationship of impulse functions to step functions. I can go into the formulas and change the values of a number within the formula. I can change the resonant frequency. I can change the damping coefficient that's in the circuit. I can change the gain constant K. You can play around, but you can see it's sort of a space that allows the students to freewheel and be able to get a good, strong visualization. And these, again, this is just one example of the types of resources that you can Google from all these places. Ken has a rich suite of resources on his website, and the Mobile Studio site. That's still up there. Yeah, the Mobile Studio site has a whole pile of materials that we tried to be able to put together and consolidate. And now, here's my parting message to you, and that is, I couldn't be more pleased that you all agreed to be able to share your knowledge and what comes out of this with folks that are trying to be able to do a similar thing for the schools in Puerto Rico. But what you represent that's actually very different is now a social structure, a community of practice that's actually built around trying to be able to improve the teaching of electrical engineering. And the tighter you stay as a community, I think you'll find the more benefit that you're able to garner, and the better you're going to be able to keep your finger on the pulse of what's taking place. I established a long-term relationship with Mohammed and Craig and Yakov and Ken and folks at Rose-Hulman. And this was a community that was built from 4 or 5 people. We expanded it out. Now it's, all 13 HBCUs that are involved in this. Take advantage of this group of folks to be able to leverage your total abilities. If you're able to do so, people will sit up and take notice. And again, I think you have the potential for being able to change the world. So with that, I'm going to quit. And I have to, unfortunately, go back to NSF because I would much rather be here. But I'll try and be back on Thursday, and I'll try and be able to share with you some of the NSF opportunities that you might want to consider building upon from the activities that you have here. So, Mohammed, with that.